Let's start here with the second part of the Week 10 Class 2 lecture. We're going to recognize that the equation shown in red here is equation 7.7 from the textbook. And I'm going to start by making a note that a part of the operator depends only on r, that is the first term and the third term, and a second part of the operator, the second term, depends only on theta and phi. We are going to use our separation of variables approach, and we recognize that psi is equal to our radial function multiplied by our y function. We're going to find that the y function is the same function that was described in chapter 6. From time to time, I may forget to write the following, and so for that reason, let me just state this up front. What we're going to do is insert this into the Schrodinger equation, and typically we divide by that same function as part of the approach that we learned in chapter 2 regarding solving using the separation of variables. Another way of putting this is to say that we're going to insert equation 7.9 from the textbook into equation 7.7. We also will note here, again, a way of simplifying our expression ultimately by recognizing a solution obtained from chapter 6. Let me rewrite this fully. So here is equation 7.7 with the radial function and the angular function written into it. What we're going to do as a variation to the separation of variables method is we're actually going to divide the expression as shown. So this expression here, we're going to divide that only by the y term. And I'll explain why shortly. And from that we get the following. And we can now write this a little more simply as follows. In fact, we're going to divide through by 2 m sub e r squared. And from this, we recognize what we're going to call the radial equation. Just to be clear, our typical method of separation of variables would have us divide by the full expression, and I recommend this as an exercise. And what we would find would be, I'll provide the result, but we'll find that we have a result as follows. This is another form of writing the radial equation. Note the difference here is that I'm writing explicitly the potential in terms of the fundamental charge on the electron and the proton. This is essentially the same equation from the box in red shown above. The more important thing at this point is to show the angular equation. And again, I'm going to jump to the conclusion, because if we take this angular equation, we'll find that this is the same angular equation that's described in chapter 6. And if we look on page 270, we'll find that when we separate the y value, of course the y term can be written up into two functions, one in theta and one in phi. When we do that, I'll write down the equations that we end up with. Again, we apply another separations of variables approach to this. You've seen this in chapter 6. We would end up with two equations, which I'll draw here for you, that should seem very familiar. And really the main point here is, since we've already studied the spherical harmonics and the rigid rotator, the only incremental work left to be done is to explore the radial equation. After going off on a little bit of a tangent here, I'm going to rewrite equation 7.10 for you, and I'm going to break down that equation into 4 different terms. Remember, of course, that m sub e is the mass of the electron. This first term we are going to call the radial kinetic energy. The second term we're going to call the angular kinetic energy. We have the potential energy, and of course we have the total energy E. As with all of our more challenging Schrodinger equations, we don't go through the solution in class. But once we solve these Schrodinger equations, we recognize that we have an eigenvalue equation. We recognize that the energy must be quantized in order for the solutions to be acceptable. So these are the definite quantized energies. E sub n is equal to minus m sub e, e to the 4th over 8 epsilon naught squared h squared n squared. We can also write that in terms of h bar. Most importantly, we recognize that n in this equation is the set of quantum numbers. These are integers from 1 through infinity. If we recall the Pogel exercises, we recognize that there is a Bohr radius to think about. And that Bohr radius is given as follows. So that Bohr radius is made up of a collection of universal constants, and therefore E sub n in terms of the Bohr radius is equal to minus E squared over 8 pi epsilon naught a naught n squared. And again, we'll make sure we write down the quantum numbers. We note that the Bohr model of the hydrogen atom, that was in chapter 1, also gave the same energies. And we also found these energies in the Rydberg equation. And that reminds us that this quantum mechanical treatment gives us the same result as was found in the empirical measurements from the early 1900s. If we compare the Bohr model of the hydrogen atom from earlier chapters, we must recognize that no longer are the positions of the electron sharply defined. And this is important because in that early Bohr model, those positions were sharply defined, and now we recognize from quantum mechanics that there's a probabilistic element to this. We can't say exactly where the electron is, and therefore these positions are not sharply defined. So the solutions themselves to equation 7.10 are called the radial wave functions, and they depend on quantum numbers n and l. And I'm going to provide a general expression for those wave functions.